Okay, welcome to this session. My name is Simone Severini, and I work in quantum technologies at AWS. Quantum technology is a new interdisciplinary area, and today we will look into what we are building in this area together with our customers and with our partners. Now, this session is divided into 3 parts. I will talk for about 10 minutes. Then I will leave the stage to Scott Buchholz, Global Quantum Computing Lead at Deloitte, and then to Oscar Painter, Director for Quantum Hardware at Amazon Web Services. Following Oscar, I will conclude this session myself. So now my job here is to set the stage, and I want to start with a question to put all of us on the same page. What is quantum technologies? What is quantum computing? Quantum computing is a new way of processing information. And quantum computers are machines that encode information in nanoscopic objects, very small objects, like, for example, photons or electrons or atoms. And these are objects whose behavior is governed by the laws of quantum physics, which is a very successful physical theory. So now, because of phenomena that occurs in that physical regimes, there is compelling evidence that there are some computational problems that can be solved efficiently by quantum computers, but cannot be solved efficiently by any other type of computer. And when I say efficiently here, I mean in a plausible amount of time. What are these problems? So first of all problems that are related to simulating quantum physics itself, like molecules, simulating material science, chemistry problems that are applied in pharmacology and biotechnologies. And solutions to these problems could impact our lives. But you see, building a quantum computer, it's really, really difficult because it's hard to control nature at the regimes of quantum physics, at the regimes of quantum hardware. And we don't know yet how to build a quantum computer at scale. Nobody knows, but both the scientific community and industry are innovating. New discoveries are published with a certain frequency, and to me, at least, is an extremely exciting moment to be in this area. So this was the first slide, which I was saying what a quantum computer is, new way of processing information, and there are 3 important points in here that we need to keep into account. This new paradigm for computation, and potentially faster for certain problems, but it's very difficult to build quantum computers. Let me move to the next one. So the next question that I was asking is, where is quantum computing today? And you see, people are building hardware and articulating use cases for let's say, what is called for the quest of practical quantum advantage, that is, using a quantum computer to solve some problems in a better way than any other type of computers, as I was saying a second ago, maybe faster or maybe even saving some energy. But the elephant in the room, I like this picture quite a lot, is that today, quantum computing still hasn't demonstrated to bring advantage in business yet. And the available machines built so far are at a stage of prototype and are important for scientific reasons, first of all, and in fact, are important to learn more about quantum computers themselves and about how to build more powerful quantum computers in the future. And however, here I like this quote at the bottom of the page by Marco Pistoia. Marco runs research in quantum tech at JP Morgan Chase, and he was here on stage at re:Invent last year. If a company doesn't do anything about the market right now, when quantum advantage becomes real, it might be too late. So it's early, but it's important to keep an eye on the technology. And at AWS, 90% of what we built is about customer problems. And given this, what is AWS building in quantum computing? What are the customer problems that we are trying to solve? And here is back in 2019, customer really told us that they wanted a one-stop shop for exploring quantum computing. And customer told us that they wanted to understand what is real and what is not about this new technology. And they wanted to do this in the AWS environment they are familiar with. And this is the reason we launched Amazon Braket. So Amazon Braket is a fully managed quantum computing service. It's in general availability already since August 2020. And you could use it today from your laptop or cell phone, for example. And Amazon Braket offers already access to quantum computers built today with different approaches. It offers access to all the resources needed to design algorithms for quantum computers, And to simulate quantum computers, of course, to some extent, because at some point we expect that quantum computers will not be simulatable anymore with conventional hardware. It's pay as you go, and its goal is really to help accelerating innovation in this space. What are the quantum computers available today on Amazon Braket? There are 5 different types of quantum computers in general availability. And this organization, you see, they don't need to worry about building infrastructure for reaching their customers or accessing or for having their quantum computers on the cloud. So we've done this for them. So IonQ, a startup from Maryland, building machines based on ion traps. Braket, a startup from Berkeley, California, building hardware based on superconductors. Oxford Quantum Circuit, a startup from Oxford in the UK, building processor based on different superconductive technology. And Xanadu, a startup from Toronto, building quantum computers based on light. Very interesting. And finally, QEra, which is a spin-off of Harvard and MIT. They're building quantum hardware based on a special type of atoms. And we will keep adding and replacing quantum hardware as this technology continues to evolve. What is the software stack? So here we provide quantum computers to customers today. You can access them today. OK, how can you program this machine? How can you code these machines? There are several layers. We want to provide the tools that enable builders operating at different levels depending on the application. And people familiar with machine learning, for example, can code this hardware using Jupyter notebooks. People that want to stay closer to the hardware can operate at a lower level of the stack, and they can program at a lower level using an assembly language such as OpenQASM, or directly using APIs. And this prompted me to move to a second customer problems that we are trying to solve, which is this one. So customers need quantum hardware integrated with cloud resources. And I believe that you see, it's difficult to look at quantum computers as independent of the cloud. And builders, customers want cloud resources when working in quantum computing. And we have learned, and we believe that for quantum computing to be successful, it's important to figure out a tight integration with conventional cloud computing resources. And it's interesting because this perspective provides customers an environment to build on AWS, where Amazon Braket is part of a much broader set of tools. And Amazon Braket, first of all, people familiar with this terminology, is serverless from day one. We built it serverless. And we built it serverless in 2019. And second, it's really integrated in the fabric of the AWS services so that customer can focus on quantum computing rather than data storage, security, notification, reporting, and analytics, and so on. And Braket, you see, as part of an orchestration layer, together with AWS Parallel Cluster, AWS Batch, AWS ECR, Amazon Braket orchestrates quantum hardware and conventional resources. And for some workflows, Amazon Braket breaks down problems into tasks for a specific type of processor and then does resources as necessary. And I think that this is very interesting because this is integration of quantum computers in the cloud, even if quantum computers today are at the stage of prototype, even if it's very, very early. And you see, this integration is not really wishful thinking. It's something that we have done today. We are building it today. So it's still very early days in quantum computing, but it's very much an exciting area. There are many quantum and non-quantum problems that we need to solve to turn this technology into an impactful reality. And of course, given this landscape, preparing customers for the future is really, really fundamental. And I'm excited to welcome here on stage Scott Buckles, a global quantum computing lead at Deloitte. And Scott will tell us about how Deloitte is working together with their customers today. Thank you.
Thanks, Simone. OK, so it's great to be here today. It's nice to see all of you. It's always fun to have the privilege of being between two PhDs in physics, because I get to be the one who tries to explain things in words that most of us can understand. But first of all, Deloitte, for those who may not know, is actually a $60 billion professional services firm. We have hundreds of thousands of people who work on problems across the spectrum of technology every day, all day. And we've actually been exploring quantum computing for a few years. You might ask why. Part of the reason is because we believe that quantum computers represent a step change in the way that we think about computing. I'll tell you a little bit about what that means and what that looks like. I'm going to try to give you some analogies. And this hopefully will be helpful for you as you think about what it is that we do, how we can help you working with AWS to accelerate your respective journeys in terms of understanding quantum computing where it is today, understanding where it's going in the future, and thinking about what is the journey that you want to go on and how you want to think about it. We do today prototypes and proofs of concept with organizations. We support education, and we do a variety of other things besides. So always happy to help. If you have questions after this, I'm easy to find. When people talk about quantum computers, a lot of times, many of us have this analogy, we're building the next generation of supercomputers. It's going to be like the computers we have today, only more so. And the answer is probably not really. So hold on a moment, and I'm going to share with you a different way to think about a quantum computer. I want you to imagine soap film. So for those of you who remember blowing bubbles as children, right, you get the little bubble thing, and you get the little wand, and you blow the bubbles out of it. Now, what happens when you blow a bubble is every time it comes out as a sphere. If you took the world's most powerful supercomputer today, you could do a whole lot of math. You can simulate all of those individual soap film atoms and the interactions and all of the forces and everything else, and after a few days, that computer would pop out, yes, indeed it will show up as a sphere, right? Because there's a lot of math that needs to be done to simulate that set of interactions. When you blow that bubble, though, that soap film is not doing a whole bunch of math. It's just following the rules of physics, and it settles into its most comfortable shape, which just happens to be a sphere. And it does so almost instantaneously. That's because the soap film is using physics to figure out what shape to be, as opposed to math. And all of the computers that we have in existence today, all the things that enable all of the technology we see and the video and everything else, is all digital. It's all math behind the scenes. So now we're using physics. The challenge is, it turns out to be really hard to figure out how to map a problem onto physics. We're really good. We've spent 60 years figuring out how to map problems onto math. We've gotten really good at it. We are not yet really good at figuring out what problems can be mapped onto physics. But a quantum computer works based on physics. So by the way, it also doesn't have memory. And there are a whole lot of reasons for that. They have to do with quantum mechanics and other exciting topics. But the reality is, it just works differently. And so that's something that's really important to know, is part of the reason when we stand up here and tell you it's important to start your journey before everybody gets there, if it's important to you, is actually because you have to learn a completely new way of thinking. There's a whole bunch of limitations and other things you get to learn that show up. And if you think a little bit about my analogy for a moment, what you will realize is a lot of the things that people tell you about quantum computers aren't quite true. You'll often hear they explore the universe of parallelism and spaces and all sorts of other wonderful things. A soap film doesn't decide whether or not it wants to be a cube before it becomes a sphere. It doesn't evaluate the universe of possible things. It just collapses to the lowest energy state. And a lot of times what's happening is, in these quantum computers, we're doing the same thing. So that's one of the reasons why quantum computers are really interesting, because we're starting to figure out that there are problems that we can map to them that we can then solve almost instantaneously. Some of those problems are things like optimization, right? How do you come up with the best answer more quickly? Some of those problems are machine learning. How do we, turns out, there's reasonable evidence to believe that quantum machine learning will actually be able to train faster with higher quality than our best comparable classical techniques. It's also, as Simone mentioned, really good for modeling chemistry and molecular simulations and other things. These are all really, 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 really hard problems. And so we are actively working across the global community to figure out how do we get better at doing these things every day as we go along. There are billions of dollars being invested globally in terms of organizations trying to figure out for themselves, what does this mean for us? Whether it's in financial services or chemicals or pharmaceuticals, whether it's governments or auto manufacturers and people managing supply chains, we see lots of organizations doing this. And that's because there are business problems where, if we could solve them much faster, have actual material value. Right? So if you can identify problems where the ability to solve them much faster generates material value, then suddenly quantum computers become quite interesting. Of course, as I said before, we still have to figure out how to map those problems onto physics. Some of this is all about getting ready. And because of that, what we've actually found, for example, is it can actually take a year or two to cross-train people from classical backgrounds and data science backgrounds to understand and be productive in terms of how to do those same tasks on quantum computers. And not everybody makes the transition, because it's going from a world that many of us are very comfortable with. I've only spent 4 decades programming classical computers, to something that's quite different on the other side and behaves quite differently. And so it's an interesting journey, and I would encourage all of you to think about it. One of the other things I'll tell you, because I like giving people analogies, so my little soap film analogy is to help you remember that these are not just the supercomputers of today, only more so. Oscar's going to come up here and tell you about, I expect, some of what Amazon's been up to. But a lot of what Simone mentioned is people are trying to use atoms and photons to build what we call qubits, which then become our basic units of building blocks for quantum computers. And it turns out, here's another analogy, that building a qubit and stringing them all together is a lot like trying to take a field full of toddlers. So imagine each toddler is a qubit. I don't know if most of you probably have experience with toddlers. They don't sit still very well, and they're really chatty. They like to talk to everybody. Turns out atoms are exactly like toddlers. They don't like sitting still, and they can't stop talking to everybody else that's all around them. In order to make an effective quantum computer, you have to get them to sit still. With atoms, we do this by cooling them to temperatures colder than outer space, or by zapping them with lasers in really, really clever ways. So you get them to all sit still, and then you have to get them to talk together in very particular ways. So imagine I have this field of toddlers, hundreds or thousands or millions of them. I've got to get them to all sit still at the same time. I've got to get them to only talk to their friends in the way that I allow them to talk to their friends. And I need them to actually do so for a long period of time, sitting still, doing useful work. And that is the challenge today of building a quantum computer. Because if you've ever watched toddlers, all it takes is somebody giggling, somebody fidgeting, and the whole system breaks down. And we have cool physics terms for all of these things. The period when the system just, everybody breaks down and all the toddlers can't sit still anymore, that's decoherence. And the amount of time that things come in is noise, right? That's everybody wanting to be chatty. So I've told you a little bit about soap film. I've told you a little bit about toddlers and qubits. No AWS presentation is done without a representative architecture diagram. So here is one. This is something that we've actually built working with some of our clients. So it's a model that we've used. And the idea that we had at the time was we were testing machine learning algorithms. So our customers had a problem. They were using classical machine learning, or they wanted to explore classical machine learning. We decided that we would also work with them to explore quantum machine learning. The interesting thing, or the thing I will tell you, is because of the toddler phenomenon, quantum machine learning models don't work as well today as our best classical models. And so what's happening is we wanted to be able to watch the increase in quality of the quantum machine learning models over time. And in order to do that, we needed something where we could repeatably deliver data to the system, run it against the best classical models, run it against the best quantum machine learning models, and figure out and track over time the progress that we were making and seeing as time went on. And so this is actually an architecture that represents one of our attempts to do that, or one of our times doing that. And part of this one was actually configured so that you could drop your data set in an S3 bucket, that there was a bunch of automation that took it through all the various classical and quantum algorithms, that reports came out the other end, that there was a cloud formation stack to make sure we could stand it all up and tear it all down when we didn't need it. And it turned out to be really useful. The nice thing, by the way, about working with AWS Braket across a variety of things is, first, as Simone mentioned, you get access to a bunch of different hardware, and more importantly, in some ways, different types of hardware. It turns out that an ion trap system works very differently and has different characteristics than a photonic system, than a superconducting system. They're all slightly different, and those differences become a big deal when we're trying to do real work. The other thing that happens is AWS is integrated in the entire AWS ecosystem, as you can see. That's really nice for me because it means I don't have to go negotiate another set of license agreements and another set of this and another set of that. Those of you who work with large organizations may appreciate the fact that every time you want to work with a small startup, it's a lot of time and energy invested. And the lovely thing about AWS is not only is all the data in one place, but it's really easy to connect it to the back-end systems and just get work done, as opposed to spending all of the time doing everything else in the meantime. So this is a little bit of the kinds of things that we've been up to. What I would offer is we will be doing sometime early next year an event jointly with AWS. So for those of you who are curious to learn more, you can send us an email if you want to scan the QR code. What we will do is we'll let you know as soon as our event planning is finalized. Really exciting. I'm always happy to answer questions. You can find me during the session afterwards or what have you. It's a pleasure talking with all of you. And now Oscar is going to talk about AWS and what they've been up to in terms of hardware.
All right. Good afternoon. Thanks, Scott. So it's my job to maybe instill a little bit of a dose of reality into this conversation. But my purpose really is to demystify what it takes to build a quantum computer. So I'm going to walk you through sort of the anatomy and the intricacies of building a quantum computer in my talk today. There's a lot of excitement around quantum computing, and rightfully so. There's also a lot of hype. At AWS, in our quantum hardware program, we're focusing on building practical quantum computers, ones that can compute commercially relevant computations at significant quantum advantage. And so what's it going to take to build such a machine? So we've come up with 4 criteria. So the first criteria is that we need to have a quantum computer, quantum processors, that have upwards of 100 logical qubits. So qubits, again, are these superpositions of digital 0 and digital 1. And we only need 100 to map on important problems, large-scale problems, due to the exponential scaling of a quantum computer. 2, we need to implement a universal gate set between those qubits. So this allows us to build a general-purpose machine, much like the digital classical computers we use are general-purpose machines. 3, and this is the trickiest part, we need to be able to have that quantum processor perform very deep circuits. So all of the algorithms that we know today that provide this sort of practical quantum advantage need a circuit depth of about 1 billion. That means we need to operate gates, different gates, one after the other, on all of these qubits 1 billion times before we can actually get one of these useful results. And we need to do that in an error-free manner. And 4, because the depth of those circuits is so large, we need to clock our quantum computer at a reasonable rate. A reasonable rate here, if you take 1 billion gate steps, is something like tens of kilohertz. That means you could compute those sorts of problems in something less than a day. So the most demanding of all of those criteria is the gate error rate. So let's just do a simple calculation. 1,000 qubits, a billion gate steps. That means we need an error rate of 1 e to the minus 12. All right? Current state of the art is a few tenths of a % error rate on our gates. So we are 9 orders of magnitude away from a practical quantum computer. So I'll let that sink in. That's the dose of reality. 9 orders of magnitude. All right? That's a challenge we have in front of us. So how are we going to do it? Well, we're going to throw the kitchen sink at it. We're going to try to do everything, right? We're going to try to reduce the noise from the environment on our quantum computer. We're going to try to improve the qubits at a fundamental physical level. But most importantly, and this is the direction we're taking AWS, is we're going to work on new architectures that involve quantum error correction. So quantum error correction allows you to detect and correct for those errors at the physical level. And importantly, it's an exponential lever. What do I mean by that? Small incremental linear improvements in the physical gate error rate allows us to realize logical gate error rates that can be exponentially smaller. And that's the only way, in a reasonable amount of time, we're going to close this 9 orders of magnitude error rate gap. Okay, so that's the challenge. Now, quantum error correction is actually pretty tricky, all right? At first, people didn't even think it would be possible. So let me tell you a little bit about the types of errors that occur in quantum computers. So I told you that our physical qubits are superpositions, weird quantum superpositions of digital 0 and 1. So there's 2 types of errors that can occur. We can have a bit flip, which flips this 0 to a 1. We can also, in quantum mechanics, because we have this superposition principle, we can actually have a phase flip, where the superposition of 0 plus 1 flips to 0 minus 1. So unlike in classical systems, we have 2 types of errors to deal with. Now there's an even more confounding problem. And that is in quantum mechanics, we can't, in one single shot, measure the state of an unknown qubit, okay, with perfect fidelity. What happens is, when you go in to measure the superposition of 0 and 1, the qubit decays into 0 or 1. And so we lose some of that information that was contained in that superposition. So if we can't look at the data and measure it, how do we know if there's an error? Right? And that was why people didn't think it was possible at the beginning. But it turns out you can do that. And it's much like classical error correction, okay, which is actually a ubiquitous technology that's used in, for instance, high-density storage. And so the way you do it is through redundant encoding. You take blocks of physical qubits, you encode just a single logical qubit into that block of physical qubits, and then you don't measure what the logical qubit state is in that block of physical qubits. Rather, you just measure whether there's been an error in any of those physical qubits. And those 2 things are different, all right, physically. So we can get around this issue. But it still comes with a severe penalty. And so if you look at this plot I'm showing you here, it's very severe. So on the y-axis is the physical error rate in our qubits. The x-axis is an overhead factor. That's how many physical qubits we need to represent a single logical qubit. And what we see here is that we need to drop the physical error rates, all right, below something on the order of 0.1% or 0.01% before we can have a reasonable amount of overhead, all right? And the overhead is still not small. It's like a factor of 100 to 1,000. So that's our big challenge. We're going to have this big overhead factor, and we need to drop our rates beyond the state of the art, not by 9 orders of magnitude anymore, but only by a factor of 10 to 100. So that's the big benefit of quantum error correction. Now let me tell you about the specific type of hardware we're developing at AWS. So it's built around what are called superconducting qubits. And these are nothing more than superconducting thin films on a silicon wafer or a silicon chip. We pattern those into inductors and capacitors. And then you can actually, at very, very low voltages, tens of microvolts, these little inductor capacitor oscillators oscillate. And you can actually create, if you add in one other element, what's called a Josephson junction that I'm showing here on the right, this Josephson junction adds just enough nonlinearity, okay, to that inductor capacitor oscillator such that at microwave frequencies I can separate out a state 0 and a state 1 from all the other amplitudes okay, in that oscillator. Now again, these amplitudes are tremendously small. They're about 10 microvolts. So they're about 100,000 to 1,000,000 times smaller than the digital logic in your laptop or your computer. All right? But what's beautiful about this is that the way we fabricate these circuits, the way we can design them, is very similar to what we do to make all the chips that are in our cell phones or in our laptops and in our computers. All right? So there's a great deal of flexibility and power behind that. In addition, the gates are fast, and the readouts have high fidelity and also fast. So it satisfies many of the criteria that I mentioned for a practical quantum computer. But we still have to improve the physical qubit performance. We need to make this jump of about a factor of 10 or 100. And so how are we going to get there? Well, really using 3 techniques. One, we need to explore new physical qubits. All right? We are not at the stage of maturity where we can say this is the qubit technology that's going to win the day. 2, we need to focus on materials development. All those billions of man-years that went into developing transistor technology, we need to apply that same level of materials development to these sorts of superconducting qubits. Right? All of the noise and errors that are in current superconducting qubits are dominated by defects in the material at this point. And second, we need to make these circuits more manufacturable. Or thirdly, so in addition to physical qubit development, we also need to have an eye on an architecture where those physical qubits can be implemented as logical qubits in a quantum error correction scheme. It's critical. We need to think about that now, not later. And so there's a number of schemes that are out there. One can take physical qubits, as I mentioned, put them into a block, and encode a single logical qubit. One popular way of doing that is this 2-dimensional array of physical qubits, a lattice, 2-dimensional lattice that you can print onto the surface of your silicon chip. And this is called a 2-dimensional surface code. It's one of the ways that we're exploring to build a logical qubit. But there's others. One other way is what's called a bosonic quantum error correction, quantum error correcting code. And so that goes back to the oscillators, where we have many different amplitude levels that I told you about. And it turns out that if you manipulate those levels in such a way, you can actually encode a qubit, okay, into those levels of the oscillator, as opposed to just limiting yourself to individual qubits and blocking them together. And the types of qubits, states that you can arrange are what are called cat states. So these are rather large macroscopic oscillating states, electrical voltages inside of your circuit. And that's why, and then you have superpositions of them, and that's why we call them cat states in analog to Schrodinger's cat. So we've made quite a bit of progress with these types of bosonic quantum error correcting code systems. And one of the unique features is that I told you there was 2 types of errors, bit flips and phase flips. It turns out that the bit flips can be exponentially suppressed in these systems. So this is some data from the lab that shows you that on the y-axis, this is the bit flip time, and this is the amplitude of that cat state. But when we linearly increase that amplitude, we get exponential suppression of the bit flip errors. And so in this case, we've increased the bit flip time by 5 orders of magnitude. All right? And this shows you the power of these sorts of new types of techniques. And we're now working in the lab to take these cat qubits and create an outer quantum error correcting code, now a much simpler one that only needs about 10 times less resources to correct for the phase flips. So in addition to work on physical qubits and logical qubits, we also have to just figure out how we're going to scale these systems. I told you quantum error correction has a penalty. It is an exponential lever, but it means we're going to have to scale things by another factor of 1,000 at the physical hardware level. So how are we going to do this? Well, we've got to figure out how to route signals on our processors. So we need to go 3D with our chips. We need to figure out how to go very large processor die and package those appropriately. We need to figure out how to connect these processors more efficiently. And fundamentally, even if we do all of that, we're likely not to be able to make processors that have more than 1,000 qubits. But I told you we probably need 100,000 or 1,000,000 physical qubits. So we're going to need to figure out how to scale out these processors and connect the different processors, the edge qubits of these processors. All right? And that's going to probably be the biggest challenge we face in scale out for quantum computers. In addition to the processors, we also have the surrounding infrastructure. we need to shield these processors from noise, and so we use dilution refrigerators to do that. We also have cryogenic wiring. Here, this is mainly an engineering problem. This is the one we can solve. But right now, it costs a lot of money, and it's very energy inefficient. So in addition to doing this scale out, we need to figure out how to drop the cost and make them much more energy efficient. Finally, I've talked a lot about hardware, but the software stack is going to fundamentally change with quantum error correction. The way you program a quantum error corrected computer is fundamentally different, right? Current quantum computers, the way they work, right, is all you do is you calibrate your processor, you bring it up, all right? You then feed it some initial data, okay, the qubits, you prepare them. You then send a series of operations to click through the gate operations you want to perform. Then you read the qubits at the end, and that's the end of your computation. In a quantum error-corrected computer, you need to continuously monitor across all the physical qubits whether there's an error. You need to decode that error, okay, if you see one. And then you need to feed back at low latency and correct for that error, all right? That's going to require a tight integration of software and control hardware. Ultimately, in addition to requiring a new type of operating system, what it's going to mean, and this is really important, is that the classical software is never, our classical compute is never going to be divorced from quantum compute. All right? They're going to be joined at the hip, and as we go forward, we're going to need more and more classical compute power to perform quantum computations. All right, so we have a development path. I'm just going to show it here briefly. We start with the logical qubit. We move all the way up to thousands of logical qubits, right? There's some important milestones along the way there where the logical gates are better than the physical gates. We can target some important applications along the way at the sort of 100 logical qubit level I mentioned. There's also even bigger and better applications that are available if we can scale those systems up even beyond 1,000 logical qubits. Along the way, we're going to continue to improve the physical hardware. And this is an important point, and this gets to what Scott and Simone have been saying, is that we also will be developing algorithms. All right? Right now, we do not have enough algorithms in terms of figuring out how to use a quantum computer. And I mean here that we're not just going to develop the algorithms in terms of making them better and more appropriate for the new architecture in quantum error correction. I also mean the development and maybe the discovery of new algorithms that we can use that we didn't even realize for certain applications. And this gets to the point that Scott was making. This is critical. This is an area of research. This is not a solved problem. Okay, and so with the last couple of slides, I'm going to zoom way out. All right, I've shown you our development roadmap and talk about a new area that we're developing at Amazon, all right? And that is in the area of quantum networks. So if I want to take, I told you that what was critical was we're going to need to scale out our processors, all right? Well, quantum mechanics not only says something and changes the game when it comes to quantum computation, but the quantum laws of nature also change the way in which we share information and collect information, all right? And this is what quantum networks are about, all right? And I'll give you an example in quantum computing. You can actually submit a job, have it computed on a quantum computer through a quantum network, receive the result back, and fundamentally do that in private, all right? That's very different than any way we do things today. Another thing that's different is that if I build a cluster of computers, right, let's say EC2, right, I have this elastic scaling. I get as I scale out the elastic system linearly in terms of the number of computers I have, I get linear increase in performance in an ideal scenario. For a quantum computer, it's exponential. If I have a quantum network, all right, so if I take a quantum computer and I add it to a cluster of other quantum computers, it doesn't just add +1 to the power of my quantum computer. It doubles the power of my quantum computer. All right, we have exponential scaling if we have a quantum network. All right, so we're very excited about this, and in fact, we've announced this new center for AWS Center for Quantum Networking. This was announced back in October, and you can read here, if you scan the QR code, you can read it in the blog. So I'll end my talk here, and let me pass it back to Simone, who's going to take us from the future that I've sort of given you, where we need to go, how hard it is, and he's going to come back to present day and tell us about what we're doing with customers right now.
Thank you, Oscar. So thanks, Oscar. Thanks, Scott. So you see, global system integrator such as Deloitte deeply understands business, and we learned from Scott that they're exploring use cases for quantum computing and preparing enterprises to upskill their workforce. And we learned from Oscar about the complexity associated with building a quantum computer at scale. That's a very difficult problem. Sometimes we talk about the engineering, but there's still a lot of science to be done there. So we need to set the right expectation. And now in the final part of the session, I'd like to go back to customers and focus on what we are actually learning by talking to customers and see what people are doing at the moment out there. And then I think there will be some time also for questions. So I would invite you back on stage for that. So let me focus on these. So who are the customers? Who are the customers for quantum computing today? So here is what we are seeing in the market today. So there are three sets of customers: pioneers, enablers, and pragmatists. And there are enterprises out there. Think about BMW, Fidelity, JP Morgan Chase, Goldman. These are pioneers, right? They're exploring the potential of quantum computing in their business. And what do? They built their own in-house groups and establish centers of excellence to prepare for the future, to try to understand if quantum computers truly will impact their business at some point and do research. Then there are enablers that have expertise to engage enterprises and accelerate innovation. And on the other side here, there are pragmatists. Who are the pragmatists? The people that really want to solve specific problems that don't really care if there is quantum computing or there is no quantum computing. They want to solve certain specific problems. And you see what they do, they engage mostly with enablers in their journey. Now, depending on where you are in your journey, you have different needs. And this is a way for me to introduce how we are addressing such needs depending on this set of customers. And I go back to customer problems, and I did on the first part of my talk. So this is something which is a bit more recent, right? 2022. So I'll start with pioneers, right? Pioneers, researchers. Pioneers are pushing the state of the art, and they need tools to get the most out of these primitive devices, out of quantum computers. And they want to figure out quantum computers inside out, hopefully even giving back feedback to the people that are building hardware. So these are pioneers. And that's why a few weeks ago, we launched Amazon Braket Pulse. This is a feature of Amazon Braket that gives, I would use the term, gives bare metal access to quantum computers, as close as possible to the quantum hardware, to manipulate really the analog signals or pulses that control computation. And this is something that the pioneers ask us to build. And this is about two things. So first, transparency, so you can see what these machines really do at the fundamental level. And second, about trying to push the machines to their computational limits, because you can have the highest level of controls for the machine. Now, another customer problems. So still staying with pioneers. So pioneers want to explore novel use cases. You see, it's very difficult to build quantum computers. It's very difficult also to articulate use cases. And what pioneers want to do would like to understand new use cases today that they have scientific value. Because we shouldn't forget that today, as I mentioned earlier, quantum computers are primarily a research tool, a tool for doing science. So here is a customer problem. Pioneers want to explore novel use cases, and that's why, very recently, a few weeks ago, we launched a new type of processor. This is an entirely new type of processor on Amazon Braket, and I mentioned this on a previous slide. First time that a machine like this one is in general availability. So we launched a quantum computer that can solve a very specific type of problem, not every problem. So this is not a universal quantum computer, only specific type of problems. But these problems are important in physics, and this computer can make a difference in areas like simulating materials, for example. It could make a difference in the study of physics itself. And today, there are a few academic research groups around the planet that are actually working with this machine. You can access it yourself today. It's in general availability, but these research teams are trying to do some science, and I think this is exciting, and I'm very much looking forward during the next few months to see what they come up with. But this is really a new type of computer. Nothing like this has been available so far in general, well, to everyone to use. Novel way for doing computation. Let me go to another customer problem. I'm trying to move towards, so from pioneers, I move towards enablers, right? And another set of customers. And the problem that enablers ask us to solve is to provide programming interfaces to develop applications. So to move to a different layer of the stack, we move to a layer that is needed in order to make things easy, or at least to make things easier, okay? And which is programming interfaces. And here, the main thing that enablers ask us to build was a way to orchestrate quantum and non-quantum resources. There is often this term classical. Classical means non-quantum, okay? Anything else that is not quantum is called classical, meaning conventional resources. There is a number of people today talking about hybrid quantum classical computation that is using a quantum computer in tandem with conventional computers, back and forth in cycles that requires hundreds of iterations, back and forth, hundreds of times. And why there is value in building this? Really for two reasons, right? First, because there are some potentially promising algorithms that need hybrid frameworks, like this back and forth between quantum and classical computers. But second, because really, if one wants to do this by hand, it's basically impossible, right? If to do hundreds of iterations by hand. And that's why we built it. And we built this orchestration framework for classical and quantum resources. It's called Amazon Braket Hybrid Jobs. And was launched, if I'm not mistaken, was launched around re:Invent, in fact, last year. And now there is customers out there that are using these to do what specifically? To explore whether these specific quantum classical algorithms can actually bring some advantage. So still exploration. Another customer problem, pragmatists. So I've considered pioneers. I moved to the enablers. Let me go to pragmatists. So pragmatists need support to understand how quantum computing will impact their business. And I'm sure there is pragmatists in the room here as well. And these are people that want to solve business problems. And they offer, of course, work with enablers to get the support they need to understand if quantum computers will impact their business at some point. How do they get this support? So here is a slide with enablers that help pragmatists. So on these slides are companies that are building today on Amazon Braket or working together with professional services. And this is about building solutions and using Braket as part, as I was saying before, as part of a complex IT offering of AWS. But it's also about building consulting services. And the fact that out there, that we see companies that are working with customers to educate customers to run proof of concept is interesting. It's very interesting. It's interesting why? Because it brings further clarity on the state of the art, and it can give customers a reason to keep digging into quantum computing and potentially to invest, and hopefully to accelerate the field itself. And now here, just some quick examples. Top left of the page, QCware. QCware, a startup from Palo Alto. They built a platform called Forge. This provides turnkey quantum computing algorithms for data scientists, financial analysts, and engineers, and it's built entirely on AWS. And it uses a number of services in addition of Amazon Braket. So you see, again, quantum computing is part of something which is more complex that require other tools. And with these, you see, I'm close to the end of the session. I would like to leave some time for questions. But before closing, here is an important call for action. How do I get started? How can I get started? So if you're a scientist or a builder that wants to explore quantum workloads, quantum computing, you can apply for AWS Cloud credits for research. If you want to understand if your business will be impacted by quantum computing, you can engage our partners to explore use cases, see previous slides, or engage with our professional service team. We have a team, the name is Amazon Quantum Solutions Lab. It's a team of experts that can help you understanding if and when quantum computers will be interesting for you, if and when. Or you can sponsor, of course, hackathon and challenges to develop specific use cases. Here I have, I'm sorry, it's fairly small on the slide, winners announced for the BMW Group Quantum Computing Challenge, exciting opportunity, 70 submissions for to try to solve 4 specific problems that BMW Group proposed, a way to crowdsource solutions for certain real-world problems in industry and bring industry closer to quantum computing, closer to the science. And now, to conclude, now a short message. It's very early days in quantum computing, right? And we saw Oscar talk. The timeline is really uncertain still. And there is a lot of work to be done, but the technology has great potential. And the keywords, in my opinion, that really matters right now are 2, are exploration and learning. So first, exploration and learning. Thank you for your attention.